Okay, so we are now recording. So volume and surface area. So volume again is how many 1 by 1 by 1 cubes can I stuff inside? That is the capacity inside some sort of space figure, we'll call it. Surface areas on a plane figure, how many square 1 by 1 square figures can we fit inside that figure in the plane? So volume is always measured in cubic units, whatever your units are, and surface area, square units. So we're not going to, and if we were in class, this would be a lot easier to show. But one big type of spatial figure that gets studied, we're going to kind of wave our hand around, not spend a lot of time with it. We're going to title polyhedra. So polyhedra are space figures, but the deal within are the sides are made up of polygons, so which we have been studying. And anybody who has ever played any kind of fantasy role-playing game, I can't say that I was ever really into it, but I had friends that were, like Dungeons and Dragons and things like that. And you end up with a lot of dice, rolling dice, and polyhedra are definitely the shapes of the dice. Okay, there's that. Good. Son of a gun. Bear with me 1 second, sorry. Huh. All right, sorry about that. All right. So as an example, I'm just going to list out a few types of polyhedra. And kind of analogous to a triangle, I suppose. Tetrahedron. So all right, so it's four-sided and it's made up of triangles. So just imagine taking four triangles and putting them together. And these polyhedra that I'm referring to, we would refer are regular. Now remember, the term regular means for a polygon, all sides have the same length. So these are regular polygons. So in the case of the triangle, of course, equilateral. So four equilateral triangles fitted together. A hexahedron get my spelling right. Fancy way to say a cube. Six-sided, made up of squares. A octahedron. Eight, and when I say sides, we're dealing with spatial figures here. A better term for that is face. 8 faces in the case of a octahedron. A hexahedron would have 6 faces. A tetrahedron would actually have 4 faces. But again, made up of equilateral triangles, made up of squares. In the case of an octahedron, it's actually made up of equilateral triangles, 8 of them. And here'll be another one. 12 faces. Dodecahedron. In 12 different faces. In the case of a face, one of the faces there is a regular pentagon to make it up. And I'll throw one more in there. Isohedron. "20 faces, and they are equilateral triangles." So now, and this does show up on Praxis, where you are asked about what are called nets. So not a net as in like I used to catch fish or something like that. This would be an example of a net. Drawing is. Try again. Here, oh, I cannot draw a straight line. Okay, so imagine these are all straight lines. And what we have are squares. So a net is laid out flat on a plane as such, but are able to be folded to create one of these regular polyhedra. In this case, this would fold to make a hexahedron or a cube. I'm going to attempt to draw one other one a little bit more complicated, and we'll see how it goes. Well, do this one. This is maybe a little easier to draw, but all equilateral triangles. And so that would be folded up into a tetrahedron. So there, I know they'll show up on Praxis, where you're given a net, just laid out flat surface like that, and asked what does it fold up to be. So again, referred to as nets. All right, so what we really want to focus on in this section, though, are different kinds of space figures we may deal with and their volume and surface area formulas. So you're not going to have an expectation to memorize these, but to be able to use them. So when we do get to a test situation, you can pull up the formula depending on what you're looking for and be able to use it. So let's go through several of these, and we're going to start with a box. This is the only way I can really draw a box. Art person once taught me this. If I make dots like this, and then play connect dot, like such. Here. Of course, there's this one here in the back. All right. So basic old box. Now it would have a length and a width. So all these sides could just be rectangular. So you could have a different length and a different width, but you also, given that third dimension, have a depth, or what we'll call a height. The volume, so we'll use a capital V for volume of a box, and kind of like area of a rectangle, which is just simply length times width. Volume is length times width times height. Those 3 units. All right, which will give you at the end of the day cubic units. Simple enough. Now surface area, so kind of like perimeter for a polygon is just add up the lengths of all the sides. Surface area is find the area of every face and add that all up. So if I were thinking about surface area of a box, and going around, so this would be height here and height here, and this would be width, and this side would be length. I would find the area of all 6 faces. So in this particular case, you would have 2 times length times width, and that would be for this top part here, and the bottom part would also have to be the same, length times width. And basically you're going to have 3 of these. You would also have a length times height, right? So that would be this face, and then of course its corresponding face over here. And then lastly, 2 times height times width, and that would be this face and this one here. And so there would be your volume and surface area formulas. Now, if you had, now this is just for a regular rectangular box where length and width can vary, it would not be the same. And the height would be something else. Now, but if you had a cube, now we're just saying, which we call the hexahedron. A cube would have length, width, and height all the same, so that all 6 faces would be congruent. So in that particular case, if you had a cube, then you would just have one side length. They would all be the same. So you would say, take the length of any one side, because they're all the same, and cube it. And then your surface area would be S squared, kind of like length times width, but again, length, width, and height would all be the same. And there would be, again, 6 of them, 2 plus 2 plus 2. So that would be for a cube. All right. Now, at any time, I'm going to turn the page, but this stuff never gets erased. So if you need to see something on a previous page, just ask. I'm going to turn the page. All right. And I want to consider another spatial figure that's not polyhedra. We're going to call this a right circular cylinder. Right circular cylinder. All right. Again, I'm going to attempt to draw this. So think pop can. That's terrible. Try again. Man. I would give anything to be able to draw. Jeez, all right, that's a little better. A little better. All right, so that's probably about as good as it's going to get. So now, want to get what is, the cylinder part. I think is fairly enough, easy enough to understand. It's just, again, think of a pop can, but you've got a circular ends. These are definitely concentric circles, so it has a center. And if I went from that center, and so you can kind of visualize a plane at the top of this right circular cylinder and a plane it's setting on the bottom. And what makes it right, that term right, think right angle. If I drop perpendicularly down to the center here, and hit the center here, this line is at a right angle. As it hit as it comes down, it forms a right angle here. And so it's not at a kind of like this, not at a slanted angle. So it comes down and laying on a plane. So basically you can set your pop can flat down on a plane surface that is at a right angle to it. All right, probably made more of that than what I needed to. Now this length from here to here, from this center, the top circle to the bottom, it's called the height of the cylinder. So remember that top and bottom are circular. So we're going to deal with two things again. What is its volume? And what is its surface area? All right. So the volume is take the area of the circular top or bottom, doesn't matter, they're going to be the same. And remember, area of a circle, pi r squared, and multiply that by the height. So it's an easier one to remember. Pi r squared times the height. And that would give you the volume of the right circular cylinder. Now the surface area looks a little more complex, but we can put it together. It's a sum of two different areas. Now, so remember, again, surface area squared units. So you've got the area of the circles, top and bottom, and then you have the surface area going around the cylinder itself. So as far as the surface area of the cylinder in and of itself, what I'm going to do is I'm going to multiply the circumference of this circle, that is, go around the can. And remember, circumference of a circle was 2 pi r, and then multiply that by the height of the right circular cylinder. So that gives me the surface area all around this cylinder here. Then I need the area of the circle on the top and the bottom, and there are two of them. So plus 2 pi r squared. Pi r squared, again, is the area of one of the circles. And that would give you your surface area. All right. Next one on our list, sphere. And right there. Sphere. All right, so addition of the sphere here. All right, so I've got a ball. perfectly round. Now, in the middle, a sphere, defined much like a circle, is a set of points in space that are all equidistant from some fixed point, the center of the sphere. So that going out to any one point on the sphere, this distance will be the same, which that distance we'll call its radius. All right, so we want to look at the volume and surface area of said sphere. All right, so the volume. Kind of a weird fraction, 4/3. 4/3 pi r cubed. So knowing that volume is a cubic unit, that's where you can remember that one has to be, because the input is put in the radius of said sphere, and then this formula, that's going to give you the volume. So the 4/3 is a little bit harder to explain why that is there. To derive the formula, we really need some calculus and integration, which obviously we don't have, so can't do it. But that is its volume formula. Now the surface area, constant of 4, and it's 4 pi r squared. We're square units again, so r squared makes sense. But that is it. That is its surface area. Right. Let's put a divider right here. Deal with kind of another circular, except this one's just going to have one circle, and it's going to be a circular base. Come from the top here, drop straight down, hit the center of this circular base, and it's going to be right at a right angle again, line. Then so putting this thing down on a plane which is perpendicular, that would the base here would be parallel to, or this height would strike perpendicularly at a right angle, and hence it's called a right circular cone. Circular. All right, so volume and surface area here. Right here, volume. Now, again, it's hard to explain where the number's coming from, but in relation to sphere, at least we can make a little bit of sense of it. It's going to be 1/3, not 4/3, but 1/3. 1/3 pi r squared times the radius squared. So, which is again my circular area, my circular base, then times the height. Now, if the volume of a sphere was 4/3, kind of think of it as like I literally took out everything but 1/3 of it, of the sphere. So I'm not sure that is the best explanation, but it makes a little, certainly would have to be less than 4/3. So surface area of the cone really looks weird. So I'm just going to write it down, then we'll kind of talk about it. And it's this: pi times r times the square root of r squared plus h squared, and then plus pi r squared. That gives you your surface area of the entire cone. Now, the area of the circular base, that would pi r squared. So that's easy enough. This part right here is giving you the surface area of everywhere else on the cone. And where this is coming from, right here, the square root of r squared plus h squared, if I imagine coming straight across to here, that radius, that would be r. And what I have is a right triangle. And so this right here, its side length, this side right here of this right triangle, the hypotenuse of that right triangle, is the square root of r squared plus h squared, and is sometimes referred to as lateral height. This right here. So it's the lateral height and then times pi r to get you the surface area of everywhere else on the cone. All right. One more to conclude, and something I had not mentioned, pyramid. All right. Now, so kind of think over in Egypt, out on the they call the Giza Plain there. Give me 1 second. Darn it. Be right back, guys. I just spilled coffee on my tablet. All right. All right. So a pyramid, in the most generic definition, is made up of triangular sides. So all the sides are triangles with a polygon base. So the ones that we typically think of over in Egypt have a square base, but in general it could be any kind of polygonal base. And that is to differentiate with what we call, we're not really going to get too much into these, but prisms. And when you talk about a prism, for older folks, I always just say, well, Pink Floyd, Dark Side of the Moon, which on the album cover has a prism. Or just thinking that thing we can shoot light into and it refracts and we can actually see the spectrum of the colors that are visible to us, that are always there, but we only see when we refract them through a prism. But in terms of what a prism is, it's got two faces on either end, which can be any kind of polygon, and parallelograms for the sides. And that is a prism. Now, in terms of pyramid, surface area would just be simply, I'm not going to write up a formula for that because it would really depend upon the pyramid, but it's triangular sides with a polygonal base. So area equals 1/2 base times height, area of a pyramid, and then whatever polygon was at the bottom, it would be the area formula for it. Now, I'm going to attempt to, and this is definitely just an attempt. And then trying to duplicate a three-dimensional. So down, say this one has this kind of a square base. All right, so you would have a height from the top of the pyramid down to the base, hitting at a right angle. And we write the volume formula, kind of like a cone. It's got 1/3. And then capital B times H, that height. All right. And B is the area of that base of the pyramid. Okay. Area of that base. Okay. So, time this down. All right. Excuse me. So I'm going to do one example problem out of here. This is from your homework. You'll have number 8. Find the volume. So unfortunately, I can't show it to you, but find the volume of a road construction marker, a cone with a height of 3 feet and a base radius 1/5 of a foot. And it says use 3.14 as an approximation of pi. All right. So first thing is, what is volume of a cone? So remember, volume of a cone, 1/3 pi r squared times the height. Try to draw a cone here. Here at a right angle. Okay. So cone has a height of 3 feet and a base radius. It's from here to here. That radius of 1/5 of a foot. This is 3 feet here. All right. Now, unfortunately, okay, I have left. That's awesome. So appears all my calculators are at work. That figures. All right, give me a second. I'm going to need to. I have one other calculator on my computer. So I'm going to have to use it to crunch the numbers. All right, so let's put it all of what we have in the formula here. Volume equals 1/3. Now pi. The radius again was given to be 1/5 of the foot, which means yes, I will have to work with a fraction. 1/5 squared, and height was 3 feet. All right. Now, always read in the blue. How do we put the answers in? The answer here is supposed to be a decimal rounded to the nearest hundredths, 2 decimal places. So I can chunk all this into my calculator. But the one thing, and I wish they wouldn't do this, but they do. They say use 3.1. If it says use 3.14 as approximation, use 3.14. Do not hit the pi button. You could end up by missing the problem by 1 decimal place. So you're literally going to have to type in 1 divided by 3, 3.14. 1/5 squared, and then 3, and then we're going to round this off. So let me get my computer calculator here and punch all these numbers in. So we have 1/3, then 3.14. Then I've got 1 divided by 5. And I'm going to square that, or just put in 1/25, and then times 3. All right, so I'm getting to 2 decimal place. Now I get on the calculator 0.1256. It said the hundredths place, so that is 0.13. And then it'll have you put the units, and you're dealing with volume, so go cubic feet. And that is it. So a lot of these problems, it's really just being able to take the volume formula or surface area formula that we went over and putting in the numbers. Any questions on that? Okay. So the last thing I want to talk about today is not in 9.5. It's actually the problems, and there's only like 4 of them, but they actually come out of section 5.5, but there's a geometry tie-in. And so what we're going to do, turn the page. Find it. All right. I want to go back to the beginning of the semester, first day. And we talked a little bit about this sequence. Five. All right, see my arithmetic is correct. And ... All right, so you guys can chat this in or just verbally say it. What is the name of this sequence? We gave it a name. Name of the sequence. Or give me the first letter of the name of the sequence. All right, somebody's answered brave. So let's see. Okay. Too many letters down. So it's a letter closer to the beginning. All right. There was this. There it was. So if everybody can see that, that was it. Fibonacci. Yep. All right. So this is referred to as the Fibonacci sequence. And we looked at a few things. We said this sequence applies itself to just like so many things. It's really it's incredible. It blows my mind that the number of things in both our physical natural world and then man-made stuff all over the place that conform to this particular sequence. All right. Now, so I got this sequence, and I said this is going to have a geometric connection. So I want to look at a rectangle. All right, this particular rectangle that I'm considering, I'm going to refer to as a golden rectangle. So what makes it golden? What makes it golden? And more to the point, the viewing rectangle that we see the world out of our eyes is golden. So what makes it golden? When the length divided by the width, the ratio of the length to the width is about 1.62. Now, that's approximate. Squigglies there. There is an exact value. It's exactly golden when it is 1 plus the square root of 5 up in the numerator, all divided by 2, which if you punch that in your calculator, yeah, I'm actually getting my phone out now. I'm going to use it. All right, so let's see if I can. That didn't work. Try it that way. Let's 2. All right, so if you take this 1 plus square root of 5 all over 2, and I carry it out to a bunch of decimal places, I'm going to have 1.61803398887. It's irrational. So decimal form, it goes on and on and on forever. So we'll leave it there. So if I round to hundreds place, it would approximately be 1.62. Again, golden rectangle. Length divided by width is this. And again, the exact value is this. All right. So still, yeah, what is the connection? As I say, there is a direct connection between this sequence we call Fibonacci sequence and this thing we call the golden rectangle. So what is the connection? I'm going to start looking at a series of ratios of consecutive terms of the Fibonacci sequence. We're just going to look at a few. That would mean starting out, I'm going to go 1 divided by 1. That's 1. And then I'm going to look at 2 divided by 1. Well, that's 2. But you'll get the pattern here very quickly because the next one I'm going to go 3 over 2. So that's 1.5. And then I'm going to go 5 over 3. So 5 divided by 3. So that is 1.6 repeating. So the bar above the 6 means that that decimal is repeating forever and ever and ever. 1.6 repeating. So the next ratio I would look at is 8 over 5. And 8 divided by 5 is exactly 1.6. So the next one after that, I'm going to go 13 over 8. So 13 divided by 8, 1.625. Next one after that, 21 over 13. 13. All right, 1.61538 462. Let's do one more, which would be 34 over 21. Now, mind you, this keeps going. Didn't stop. I just cut it off there. So now 34 divided by 21 gives me 1.6190476 and I can keep going, but I think it's already fairly evident what this is close to is I'm looking at consecutive ratios of consecutive terms of the Fibonacci sequence. The farther I go out, the closer to the golden ratio I get. Now, if we would go on and study some more mathematics and study a concept called limit, it's basically as I would go to, because the sequence just goes to infinity, goes on forever and ever and ever. If I would look at the limit of the ratio of consecutive terms of the Fibonacci sequence, it's exactly the golden ratio. So there's an absolute direct connection between these two. All right, so I want to do one last thing with this. And it's going to involve using a quadratic formula, which we looked at last class. I want to derive this guy right here. All right, so the 1 plus square root of 5 all over 2. So I'm going to turn the page, draw another rectangle. Length and width. All right, so in addition to length and width being about 1.62, you have a golden rectangle if you have this proportion. Length divided by width equals, and I'm going to go length plus width divided by width. So if this proportion is equal, this equals this, the rectangle is golden. All right, so what I'm going to do, I'm first going to rewrite this as length over width equals, I'm splitting this into two terms. Yeah, shoot. Okay, my bad. I apologize for taking notes. That should have been length right there. Erase this. I got it right. That bottom should have been length, not width. So this equals length over length plus width over length. So all I've done is I've taken this and I've split this into two terms. Now, I'm going to make a little substitution, kind of make this thing look a little easier. If you pick up any kind of math book that talks about the golden ratio, it's usually denoted with the Greek letter phi, which looks like that. And we're going to say phi equals length divided by width. So if I go make this substitution into here, length over width, well, we said that's going to be phi. Now, L over L is 1. And this, notice, is the reciprocal. That is the flip of length over width. So if it's reciprocal, the reciprocal of phi would be 1 over phi. All right. So all I've done is I've rewritten this equation based on this substitution right here. And now I'm going to hit this with a little bit of algebra. If I have an equation, I'm allowed to multiply both sides by the same thing. So I'm going to multiply every term by phi. So as long as I multiply every single term, I still have the same equation. All right, so phi times phi is phi squared. Phi times 1 is phi. And notice here the phi's would cancel out and leave me with just plus 1. All right, so just kind of like that problem we had looked at last Thursday, I have a quadratic equation, highest power 2, where phi is the variable. So I'm going to set this thing equal to 0. That is, bring these two terms over to this side. All right, now that is not factorable. So we don't have a choice. We have to use the quadratic formula. All right, so quick review. If I have x is the variable, any coefficients a, b, and c, you can use completing the square and derive this formula. Opposite of b plus or minus square root of b squared minus 4ac all over 2a. Okay. So then, let's solve this quadratic formula. So notice your coefficients this time for the so phi is like x, it's the variable. So your a is 1, your b is -1, and your c is -1. So we're going to pop those in, right x there. We're going to pop these in the formula. So we're solving variable phi. Opposite of -1 plus or minus square root of b squared, that's -1, squared minus 4 times a, which was 1, times c, which was -1, all over 2a, and a was 1. And then we'll just simplify this as much as we can. So opposite of -1 is 1. Plus or minus square root of. Now, inside here, if I just do the arithmetic, -1 squared is 1. Here, I've got a negative times negative. That's double negation, so it turns to addition. This just turns into 1 plus 4, which is 5, all over 2 times 1, which is 2. So I get two answers here. I either have phi is 1 plus the square root of 5 all over 2, which is what we called the golden ratio. Then there's also phi equals 1 minus the square root of 5 all over 2. And so this again, what we call that golden ratio. Length divided by width of a rectangle. It's exactly that. We have a golden rectangle. So there is a problem. There's like, let me see. Quote you on this. There are 5 problems in this section. I'm going to assign just 5 problems dealing with this golden ratio and golden rectangle. But there's the last problem actually deals with that guy, that 1 minus square root of 5 all over 2. All right, any questions or anything you need to see from the whiteboard, any of the other pages? If not, I want to then go ahead. I'm assigning 9.5, which I believe there were 11 problems. So let's get it assigned. Today's the 7th. So I'll put the 9th as a due date. Students change your score. I have assigned that. And I am now assigning points. So it's section 5.5. It'll all be in order. Now, this is going to be a little confusing. And remember, I started this semester in a much different order than I had ever done before. For the reason was I wanted to be able to do geometric constructions in the classroom, which we were able to accomplish. So I'm assigning a quiz, and this quiz covers, I believe it's 11 problems, covers chapter 9, which we just finished. So on Thursday, we're going to review back through, and we're going to be ready to have our first test. And again, you're going to end up now taking it on MyMathLab and at home, and I'll give you a week window. So I'm not assigning the test yet. I'm just assigning a quiz that goes over chapter 9 or goes over the geometry unit. It's labeled quiz 3 because I normally have, this has been the 3rd unit I've covered. So don't let that throw you. It's just take the quiz. So give me a second. I am now assigning that. Again, quizzes can be done an unlimited number of times. So, but you have to take the whole quiz each time. So highest score counts. So if you take it 4 times, if your 3rd attempt was the highest score, that is your score, whatever the highest score is. And I'm assigning due date that one on Thursday as well, with the intention that I want you to take that quiz once before Thursday. So you essentially have, I'm going to double check the number of problems here. Yeah, there were 11 problems out of 9.5, 5 problems out of 5.5. So that's 16 total problems, not too bad. And then the quiz, I believe, is 11 questions. So that is the assignment for Thursday's class. And if you haven't got the geo construction, if you were in a position you needed to do that, the 2 assigned constructions, and then send me that picture, still do that. I did, as I said, I've got several of them. I have to set at some point by tomorrow and sort through those and put them in a folder. So any questions? Okay. So I'm going to go ahead. Maybe.